Okay guys, we are going to try this one more time. This is take 3. I keep having computer issues, so here we go. A lot of our real world problems involve systems of equations, but they typically have more than 2 or 3 variables. We call these multivariate or multivariable systems. Examples of things like this include air traffic control, stoplight scheduling, 3D printers, robotics, engineering problems. All kinds of things are multivariate systems that we need to work our way through to find the values that we're interested in. Now, graphing, addition, and substitution, the methods we've been working with smaller systems, would take a lot of time to do with multivariable systems. So we use matrices when we're solving multivariate systems. And a matrix is just an improved version of our addition method that we use. So it's not brand new. When we set up a matrix, we organize our numbers, just the coefficients and the constants. We don't include the variables within the matrix, into a rectangular array. Now, this first page really just gives us some definitions and some basics with what matrices look like. A row matrix is going to be a single row, and rows go left to right. So, for example, a row matrix might be 2, 3, 5, where I have one row and 1, 2, 3 columns. Our matrix size or order is always the number of rows by the number of columns. So R times C, or R by C, gives us our size of our matrix. Whatever you need to remember that rows come first, RC Cola is a thing, Royal Crown, whatever gets you in that correct order. Rows go across, columns go up and down, columns hold up the porch roof. But this particular matrix would be a 1 by 3 matrix, 1 row and 3 columns. I have 3 elements inside this matrix, and I can identify elements according to their position. For example, element A11, so I always just use an A for my element, is row 1, column 1. So the element in position 1, 1 is a 2 for this matrix. The element in position 1, 3, row 1, column 3, is a 5 for this matrix. Conversely, our column matrix has a single column. It can also be called a column vector. A row matrix could be called a row vector. Columns go vertically up and down. So an example of a column matrix might be, let's use the same 3 elements. We've got row 1, row 2, row 3, and only 1 column. So the size of this column matrix, let's keep things kind of color-coded. The size of my column matrix would be a 3 by 1 because we've got 3 rows and 1 column. That element 2 is still in the first position. Element 2 is still A11. I don't have an A13 position. That would be first row, third column. I don't have a third column. Instead, I have row 3, column 1. That's where the 5 is for this matrix. So these little subscripts just tell us the location within the matrix. Now, a square matrix, we use square matrices a lot. A square matrix has the same number of rows and columns, so that our information, our elements, make a square. Same number of rows and columns. So, for example, if I have a 2 by 2 square matrix, I'm going to have 2 rows and 2 columns. So I've got row 1, row 2, column 1, column 2. The size of this matrix, we said it's a 2 by 2 square matrix. What element is in position 2, 2? Well, that would be row 2, column 2. That would be 8 is in position, row 2, column 2. How about row 1, column 2? What element is in row 1, column 2? Well, that would be a 6. Now, when I use a matrix to solve a system, I use an augmented matrix. This is going to represent a system of equations. and I set it up so that there is one row per equation and one column per variable plus an augmented column for our constants that represent our solution. So let's see, for example, if I have the system and I want to turn that into matrix form, I have a row for each equation. I just write down, I got to talking and I messed up, guys. I just write down the numbers, and then I have a line to offset that constant, the augmented column. And I always do alphabetical order, X, Y, and then my constant. So my second row is going to be 5, -7, -1. So here I have two rows, one row to represent each of my equations, and I have 3 columns to represent my variable x, my variable y, and my constants. So that when I look at my augmented matrix, I could put it back into the system of equations form really easily. Finally, for our definitions, our identity matrix is what we are working towards when we're trying to solve a system using matrices. An identity matrix has 1s on the diagonal and 0s everywhere else except the augmented column. That augmented column is what represents our solution. So, for example, let's do a little bit bigger matrix. 1s on the diagonal and 0s everywhere else is our identity matrix. And then we're going to make an augmented column out here. So you see I've got 1, 2, 3 rows that represents 3 equations. I've got 3 variable columns and an augmented column for my solutions. My variables are going to go in order, so this is going to be x, y, z, and then my constants give me my solution. So if I were going to put this back into equation form, this first row tells me I have 1x, and that's going to be equal to 5. 0 y's, 0 z's. My second row tells me that I have 1y, and it's equal to 6, and my third row tells me I have 1z, and it's equal to 7. So I could write this as the solution to my system like this, or I could put it in an ordered triple, x, y, z. All right, let's look at our next page. Now that we have our definitions down, we're going to do some practice writing the systems into augmented matrices. For this first one, I have 2, and I apologize for the way this is set. I should have gone back and fixed my brackets. Those should be nice squared off brackets, and my math type wasn't working for me, so I had to improvise. Okay, so I've got 2 rows, which means I'm going to have 2 equations that make up my system when I write the system. So that becomes, remember I use the same order, x, y, and then constants. So I've got 1x plus 3y equals a -5. And my second row gives me 2x minus 3y equals a +1. And that's the system that this matrix represents. So pause the video and go ahead and reinterpret each of these 2 matrices as their equivalent system of equations. So pause the video and then come back to see how you did. Since this has the identity matrix on the left, this gives me my solution to that system. Remember, we always go in order x, y, z, and then we have the constant as our augmented column. That has 0 y's, so that's just plus 4z there. And there's that system of 3 equations with 3 variables. And I knew it was going to be 3 because I had 3 rows, so I knew I was going to have 3 equations. Okay. Back substitution. You can use a partially constructed identity matrix to work backward to solve the system. When I say partially constructed identity matrix, I mean that I have ones on the diagonal and zeros below. So I've got that bit of the identity matrix. I don't have the rest. Here's how this works. If I start at the bottom, this would be x, this would be y, and there's my constants. So this second row tells me that 1y equals 21. That's my value for y. My first row tells me x minus 2y equals 8. So I can take my value for y and go back up and substitute it in to solve for x. That means that x minus 2 times 21, because that's my value for y, is equal to 8. Which means when I add that 42 over to move it over and finish solving, I figure out that x would be 50. And I don't just leave those variables hanging out there, I write them as an ordered pair, an xy ordered pair to represent my solution. Another one, a little bit bigger system. We've got 3 rows, so I know I've got 3 equations. I've also got 3 variables, so that's going to be x, y, z, and then my constants column. I'm using back substitution. I've got the ones on the diagonal, almost, that's a -1, zeros down below. So I'm going to bring that out, and I'm going to say, okay, negative xy, that's a negative z equals -3, which means that positive z equals positive 3. If I divide those both by a -1 to finish solving for z. My second row tells me y minus 2/3 z equals 0. My first row tells me x minus y plus 2z equals 9. So I'm going to take this solution, this value for z, I'm going to go back up and plug it in here so I can solve for y. Y minus 2/3 times 3 over 1. 3 is just 3 over 1. That's my z I plugged in. Well, right here, 6 over 3 is just 2. So that gives me y minus 2 equals 0, which means y is a positive 2. And I'm going to take both of these values for z and y back up into my first equation to solve for x. So my first equation is x minus y plus 2z equals 9. Well, I don't know x. I do know that y is 2, and I know that z is 3. Well, that is 4. Minus 2 plus 6 is 4, so x plus 4 equals 9, which means that x is going to be 5. I don't leave those variables hanging out like that. I go ahead and I put them in an ordered triple. Now typically we keep everything in order x, y, z. Pay attention to how your book does it. It may instruct you to do things in a little bit different order, but it's always going to be x and then y. Okay. Another way to work with these matrices to get to that back substitution spot is to use what we call row operations to simplify it, and we have until we have enough of that identity matrix so that we can stop and use back substitution. I'm not going to make you go to the full identity matrix. We're going to go far enough so that we have the ones on that diagonal, 0 below, and can use back substitution. When you're working to get the identity matrix, we always want to finish the first column before moving to the next column. We'll get the 1 in the place where it goes in each column. And the way we get a 1 in place is to multiply by the reciprocal. And we're going to do some of these. It's going to make sense, but you're going to have it all written down. You're going to multiply by the reciprocal. What's the reciprocal? Well, the reciprocal of 2 would be 1/2. The reciprocal of 3/5 would be 5/3. The reciprocal means I flip that number. And then, to get the zeros in place, I add multiples of a row to replace a row. So there's only 3 legal moves that we do. We can exchange rows. If you already, remember, we want to get that 1 in position first. If there's already a 1 somewhere in your first column, we rearrange the rows to get the 1 where we want it. If I'm working with this matrix, I've got 2 rows, I've got an X column, a Y column, and a constant column. So I want the identity matrix, or at least enough of it so I can do back substitution. So I want to work toward this look where I've got the identity over here, which means I need a 1 right there in that first position. Well, I've got a 1 in my first column, it's just in the wrong row. So I'm going to exchange the rows, and my row operation instruction looks like this. I exchange row 1 with row 2. When I exchange row 1 with row 2, I end up with 1, 3, negative 5 over 2, negative 3, 1. I just rearrange the order of the 2 rows. Now that's my easy one. Sometimes I can't use it. It's not helpful. And what if I want to work with what I've got to get a 1 in position? Now remember, we're working with our identity matrix. We're going back to our original matrix that we started with. My other option to get a 1 in this position is to multiply by the reciprocal. That was what I set up here. I can multiply by the reciprocal, and that will give me a 1. Anytime I do that, I will get a 1. That instruction is going to be out front of the row that I'm working on. The reciprocal of 2 is 1/2. So I'm going to multiply 1/2 times row 1. Write your instruction down first, and then go through and apply it to that row. Half of 2 is 1. That was my goal. Half of negative 3 is a negative 3/2. Leave it as a fraction. Half of 1 is 1/2. So remember, we said that we always finish the first column before we move on. We got our 1 in position here. Now we need a 0 down below. In order to get this 0, I'm going to add multiples of rows. This is that addition method that we've done before. We use this to replace rows to get a 0 where I need it. Well, 1 plus a negative 1 gives me a 0, right? So if I multiply this first row by a negative and add it to row 2, using it to replace row 2, that's what I want to do. So a negative 1 times row 1 plus row 2, and I'm replacing row 2. So I write this instruction next to the row that's being replaced. Let me move this up so you can see me. I'm replacing row 2, so I write it in front of the row I'm replacing. I'm going to multiply 1 times my first row, and I'm going to add it to the second. Now the purpose, 1 times a negative is a negative 1 plus 1 is 0. That was my goal, and I got there. My next step, a negative times a negative 3/2 is a positive 3/2, and I need to add that to 3. Well, let's come over to the side and let's do a little side work. 3/2 plus 3, let's make that 3 over 1. I need a common denominator. So to get a 2 as my common denominator, I multiply this by 2 over 2. That gives me 3/2 plus 6/2. That is 9/2. So right there, that's a 9/2. And I'm still thinking of multiplying through row 1 times a negative, times negative 1, times negative 1, times negative 1. Well, that gives me a negative 1/2, and a negative 5 is a negative 5.5. Negative 5.5. Let's put that as an improper fraction instead of a mixed number. If we've got 5 wholes, that's 10/2 plus 1 more is a negative 11/2. Negative 11/2 there. Now remember that we want to finish one column before we move on to the next. My next step would be to get a 1 here. Do you remember how to get a 1 in position? Well, we multiply by the reciprocal to get a 1. To get a 1, we multiply by the reciprocal. What's the reciprocal of 9/2? Well, it's going to be 2/9. So let's work that out. Let's say I'm not going to change that first row. I'm going to multiply row 2 times that reciprocal, 2 over 9. Well, 0 times anything is just 0. 9/2 times 2 over 9, that gives me my 1. That's what I was after. So I've got 2 over 9 times 11/2 for this constant position. Well, that gives me, the 2's are going to cancel, and I have a negative 11 ninths. Negative 11 ninths. And we're in position to solve this system. This second row tells me this is my x, this is my y, this is my constant. The second row tells me that y is equal to a negative 11 ninths. My first row tells me that x minus 3/2 y equals 1/2. I can take this value, plug it in for y, and finish solving. Now we're not going to finish that right now. We're going to practice row operations again. We're going to rewrite the system of linear equations as an augmented matrix, and then we're going to use our row operations to get that identity matrix and solve. So the first step is to turn our system into an augmented matrix. When I turn it into an augmented matrix, no variables show up, just the coefficients and the constants. Where I have a negative, I put in a negative. Now, our goal is to get 1's on the diagonal, 0's everywhere else except that constant column, constant 1, constant 2. So my first step is to get a 1 here. Well, how do I get a 1? To get a 1, I multiply by the reciprocal. So I'm not changing the second row. I'm not working with it yet. I'm just going to multiply row 1 by the reciprocal of this first element so that I get a 1 there. 1/2 times 2 is 1. Then I go ahead and finish out my row. Half of negative 4 is negative 2, and half of 16 is 8. So I've got a 1 where I need it. My next step is to get a 0 down below. Well, how do I get zeros? I add the opposite. The opposite of 3 is a negative 3. Now we're not going to change our first row this time. We're going to change our second row. If I multiply a negative 3 by the first row and add it here, I get my 0. So negative 3 times row 1 plus row 2. Write down your instruction in front of the row you are changing. So negative 3 times row 1, that's a negative 3, plus 3 is 0. That was my goal. I need to finish out the row. Negative 3 times negative 2 is 6, plus 1 is 7. Negative 3 times 8 is a negative 24, plus 3 is a negative 21. And if you need to come over here and do some side work, or you've got your calculator and you're doing it in your calculator, that's great. Do what you need to do to make it work. So we finished our first column. We got our identity matrix in the first column. We're going to move on to the second column. We need to get that 1 in position. That's our next step, is to get this 1 in position here. Well, how do I get a 1? I multiply by the reciprocal. So I'm not changing the first row this time. I just copy it down. My goal is to get a 1 here, so I'm going to multiply by that reciprocal to row 2, and it's row 2 that I'm changing. Anything times 0 is 0. A 7th times 7 is 1. That was my goal. And then 1/7 times negative 21. Negative 21 sevenths is a negative 3. And that's all we have to do. That's all I'm going to ask you for. I've got enough to do back substitution. I've got the 1's on the diagonal and the 0 down below. So I bring this out and I say, okay, the second row, this is x, y, and constants. My second row tells me that y is equal to negative 3. My first row tells me that x minus 2y equals 8. And since I know that y is negative 3, I can go back up and substitute that in. So x, that becomes x minus 2 times negative 3 equals 8. Well, that's a positive, x plus 6. And I finish solving for x and I get 2. Now, I don't just leave those hanging out there. I say, all right, ordered pair, x, y, ordered pair in parentheses as my answer. Now, typically, I am not asking you to go all the way to solution from a fresh matrix unless we've only got a few steps like this. We only had 1, 2, 3 steps, and then we pulled it out and we did our substitution to solve. Oops, let's go back to that 3 variable system I absolutely nearly skipped. Okay, we're going to rewrite the system of linear equations as an augmented matrix, and then we are going to work on it a little bit. Now notice that I'm not going all the way. We're going to use row operations to complete the first column. My first column, if I have an identity with 3 variables, my first column is that 1, 0, 0. So all I'm after right now is this first column. I want to get 1, 0, 0 in my first column. Well, I start by rewriting it as an identity matrix. I'm going to have X, Y, Z, and then an augmented constant column. I'm going to have 3 rows, row 1, row 2, row 3, representing my 3 equations in my system. Oh, notice I don't have a Y here. That means I put a 0 in that position for my matrix. Once I get the augmented matrix set, I think about what I want to do. Well, I'm after this first column. I need to get that 1 in position first. How do I get a 1? Well, how did I get a 1 up here? I multiplied by the reciprocal. To get a 1 in position, I multiply by the reciprocal. So all I'm changing is this first row, which means I'm going to copy down the other 2 rows because they're not going to change this time around. All I'm changing is row 1, and I'm going to multiply row 1 by the reciprocal of that first element. So 1/2 times row 1. Well, reciprocal right there, 1/2 times 2 is 1. That was my goal. Half of -6 is -3. Half of 4 is 2. Half of 10 is 5. Now all I'm after is this first row. I'm working my way down. The next step is going to be to get a 0 here. How do I get zeros? Well, I add the opposite. So I'm just changing that second row this time. So I'm going to write down my first row. It's not going to change. And I'm going to write down my third row. It's not going to change. I'm changing row 2, and I'm doing that by adding the opposite. So the opposite of 1 is -1. So negative row 1 plus row 2. -1 plus 1 is 0. That was my goal, but I have to do the whole row. That becomes a +3 plus 5, -2 minus 5, -5 plus 0. That's my new row 2. All right, next row down, I need to get that last 0 in position. I need to change that 3 to a 0, so I'm not going to change the first 2 rows. I am going to change this third row. I'm going to add the opposite of 3. Well, the opposite of 3 is a -3, so I'm going to do -3 times row 1 and add that to row 3. -3 times row 1 plus row 3. Guys, give me just 1 second. Let me make sure we are still recording. My computer screen went to sleep. Okay, excellent. So this becomes a -3 plus 3 is 0. -3 times -3 is 9. -3 times 2 is -6. Plus 4 is -2. -3 times 5 is a -15, plus 7 is a -8. Now, I didn't ask you to go any further than that. I said just to get to that point. So we're going to stop there, and we are going to say that is good enough. Now, after I got started, it dawned on me that I had a 1 in position here, and I could have chosen to exchange these 2 rows as my first move. And that would have changed what things look like as I work down through that first column. So you've got options, just like with the other math things that we've done so far, you have options with how you work through these. Okay, I think this is our last page. We're going to talk about dependent and inconsistent systems. A dependent system, you know, has an infinite number of solutions. What does this look like as a matrix? We're going to rewrite this system of linear equations as an augmented matrix and use row operations to get to our identity matrix so that we can solve. So I'm telling you that we expect this to be a dependent system, and we're investigating what this looks like as a matrix. My first step is to rewrite it as an augmented matrix. And if I look at it, I know it's going to be a dependent system because my coefficients on the first row, if I multiply by 2, I get the second row. But we're going to work through it and see what this looks like when I get a dependent system. Well, what's my goal? My first goal is to get a 1 in position here. So I'm going to do half of row 1 to get that 1 in position. Half of row 1 gives me a 1, 1/2, and 2. I'm not changing row 2 yet. Now I'm going to go back and change row 2. So I'm going to copy down that first row. It's not going to change. I need to get a 0 here. I get zeros by adding the opposite. Well, the opposite of 4 is -4. So I'm going to do -4 times row 1, add that to row 2, and it's row 2 that I'm changing, so I write that next to row 2. -4 plus 4 is 0. -4 times a half. Half of -4 is a -2. -2 and 2 is 0. -4 times 2 is a -8. Plus 8 is also 0. There is my dependent system. This second row tells me 0 is equal to 0. The left side is 0. The right side is 0. This is always true. So assuming I've done things correctly, I have that dependent system. And remember, we write that solution set by saying, all right, any ordered pair x, y such that, and then I just use either one of my equations. If it fits this equation, it's going to fit the entire system. Got an infinite number of solutions. What does an inconsistent system look like? An inconsistent system has no solution. Let's see what that looks like as a matrix. So first step, ooh, that's out of order. Let's put this in order so that I have x, y in constant. If I move this y over, that becomes x minus y equals 3. And if I move my x over, that's a -2x plus 2y equals 5. All right, let's set that up as a matrix. That first row would be 1, -1, and 3. My second row would be -2, +2, and 5. All right, well, what am I going to do first? First, I get this working on my first column. I get that 0, or excuse me, the 1 in position there. It's already there. That's done. So I don't need to change my first row. I need to get a 0 down below. So let's go ahead and copy down that first row. We've got 1 where it needs to be. How do we get zeros? Well, we add opposites. The opposite of -2 is 2. So 2 times row 1 plus row 2. 2 times 1 is 2, minus 2 is 0. 2 times -1 is -1, plus 2 is 0. 2 times 3 is 6, plus 5 is 11. Apologize that you couldn't see for a little bit. My second row, what does that tell me? Well, left side equals right side. That gives me 0 equals 11, which is not a true statement. That's never true. So this is inconsistent. It's an inconsistent system, and there is no solution. Anytime I get a statement that is not true, I know I have an inconsistent system with no solution.